Yes, so hello everyone. This is lecture 5 on computer networks, and in the previous lecture we were discussing CRC scheme, cyclic redundancy check. Okay, so we were having data word, we were having divisor, and from that we tried to find the code word. What was the basic scheme? If divisor contain n bits, okay, or let me say like this: data word is of n bits, divisor is of k bits, so code word will be of n plus k minus 1 bits. Okay, so we are simply appending k minus 1 bits to the data word, and then we will perform the modulo 2 division, and remainder will be simply added, and finally n plus k minus 1 bit we will get the code word. So we have studied this technique, and in the previous lecture I have given you a very small question that whether this CRC mechanism is perfect or not. That means, is there any case where error is there and still CRC is not able to detect it? Okay, so perfect means if there is no case, okay, then we will say it is perfect. But if we are able to find a case, okay, is there exist case such that error is there but still CRC cannot detect it, but still CRC can't detect it. So if we have some cases like that, then we will say it is not perfect, otherwise we will say it is perfect. So let me tell you the basic idea. So for example, code word, okay, we have some data word, we have some divisor and all, and finally we have find the code word. Okay, so we have some data word, we have some divisor, okay, and we from the modulo 2 division we have find the code word like 101101101101. Okay, like this. I have just randomly written any binary number, so we have got this. Okay, so code word was this. When it was sent through the media, the received code word RCW, received code word is RCW, SCW is sent code word. Okay, so received code word comes out to be 11 like this. So what has happened? This 0 has become 1. This 0 has become 1. So can I write this received code word as 1011011101 plus 100? So 1000? Can I write it like this? Because if I add this, this is your sent code word. If I add 1000 to it, binary addition, so you will get this received code word. So what do you mean by this? So received code word is nothing but your sent code word. Received code word is nothing but your sent code word plus error. This is some error, na? Okay, so I have just given you 1 bit error. We can have multiple bits error and so on, whatever may be the error. So depending upon that, we can add, subtract, something like that. So basically what I want to say is, you can add or subtract something, it hardly matters to me. The main thing is that there is some error. Okay, so received code word is sent code word plus error. That is the basic thing. Now I divide it by your divisor. Okay, so RCW divided by divisor, that is equal to sent code word divided by divisor and error by divisor. Okay, so now when can I say that my scheme is perfect or not? Let me give you some idea. So if received code word by divisor, this is not equal to 0, okay, that means remainder is coming, some remainder is coming, then immediately you will say yes, there is some error. Are you getting it? In the previous lecture itself we have cleared that thing, that if no remainder is coming, then obviously your code word will be accepted, otherwise they will reject it, saying that there is some error. So if received code word, when it was modulo 2 division was done by divisor, then if it is not equal to 0, result is not equal to 0, we will say error, and we will say scheme is successful. No problem, CRC has detected the error. There is some error and it has detected it, na? So scheme successful. Are you getting it? Why we are saying scheme is successful? Because there was some error and CRC has successfully detected it. But there might be some other cases. For example, if RCW divided by divisor is coming to be 0, if it is coming to be 0, then what does this mean? That this remainder, actually from your definition only, this remainder should be 0. Okay, I think you know already, sent code word, when we will divide it by divisor, by definition itself we will get 0. Okay, so this is by definition. Let me write it. Definition itself is saying so. I'm not saying so. Definition itself is saying so that it should be 0. Now, if error by divisor, now since it is coming to be 0, that means what? Error by divisor is also 0. That's why 0 plus 0 is 0. Na? Error by divisor is also 0. Now there are two cases. That means when divisor is there and this is your error. You have divided it. Now there are two cases. Why remainder is coming to be 0? Either this error itself is 0, or this error is not equal to 0, but by chance this error is multiple of divisor. That's why remainder is coming to be 0. So if error is equal to 0, then obviously we will say our scheme is successful. No problem. Scheme is successful. Okay, because there is no error and CRC has not detected it, because since there is no error, then how it will be detected? It is not detected. Okay, so you will say, okay, my scheme is successful. But if error is not equal to 0 and error was done in such a way that when we divide it by divisor, our remainder is coming to be 0, then we will say our scheme is not successful. Scheme not successful. But such kind of error happening is really very, very difficult, because we need to do some error at particular places. Okay, for example, I'm not going into the details, I'm just giving you the intuition behind it. For example, say divisor is 11, decimal number 11. Okay, and you have sent number 33. Okay, so 11 mod 33, 33 mod 11, it is 0. But by chance received was 44. So 33 to 44, if you do the binary and all, so very selective bits will be converted to 1, 0 and so on. But so error chances are very, very less. Okay, means that scheme is not successful. Probability of this is very, very less. Okay, that's why CRC is one of the best scheme. It is one of the best scheme, and it is mostly used at data link layer for error detection. Okay, data link layer error detection, it is done by CRC most of the cases. So please let me know if somebody is having any doubt.
This is clear, sir, but I have a question.
Yeah.
How remainder coming out to be 0 ensures that it is a valid code word? Like how CRC ensures that received data is correct or not?
So we cannot detect that, na? That is the problem, na? That I'm saying that scheme is not successful. See, if error is not equal to 0, so sorry, if RCW when divided by divisor, received code word when divided by divisor, if remainder is not 0, you will say error is there. But if remainder is coming to be 0, then there are two chances. Okay, what are the chances? First chance is that error is itself 0. If error itself is 0, then your scheme is successful. But if error is multiple of divisor, or you can say when I perform a modular root division of error and divisor and I'm getting remainder 0, that means error is still there, but CRC is not able to detect it. That is the biggest problem. Okay, so in this case, clearly the scheme fails. So CRC is simply saying like that. CRC is saying if not equal to 0, we have an error and it will simply discard it. But if equal to 0 is coming, then it will simply say accept. RCW will be accepted. That's it. Okay, so equal to 0, then RCW accepted. That's it. It hardly matters whether it is wrong or correct. The scheme is like this only. So now it entirely depends on the probability and all the things that if received code word is accepted, no doubt. Now, is this received code word correct or not? That is the question, and we have answered this like this. Any doubt?
No, sir.
Yes. Yes. Please come again.
Clear, sir, clear.
Okay. Okay. Yes. Good. Okay. So now let me show you polynomial notation. Please take snapshot. I will jump to the next slide. Done. Okay. Yeah. So now we are jumping to polynomial notation. We are in CRC only. Okay. We are just going to study polynomial notation. Sometimes question have been asked in GATE from this topic also. So it is very simple. Okay. So you will get it immediately. For example, we were doing for binary numbers, na? Why binary numbers were used? Because in networking, exactly binary numbers are sent from sender to receiver only. Okay, and binary numbers, if I talk on wire, then binary numbers are not sent, signals are sent. Okay, so for that we have signal encoding schemes and all. That is the part of physical layer. I have told you, I have given you a bit idea of that also. Okay, so the basic thing is this is some binary number. Okay, so what polynomial notation is saying, you simply write it just like polynomial, x cube, x3, x4, x5, like this. So finally this is nothing but, this binary number is nothing but x power 5 plus x power 3 plus x square plus 1. Okay, this is my answer. So this binary number is converted to polynomial notation like this. Okay, similarly, if you have say binary number 101, what you will say, x power 0, x power 1, x power 2, so it is nothing but x square plus 1. 101 is x square plus 1. Okay, if you want one more example, see this now, x power 0, x power 1, x power 2, x power 3, so x cube plus x plus 1, and so on. I think you have got the point how polynomials are made and all. Okay, so now let me show you some question. So data word is given to you as x cube plus 1 and divisor is x cube plus x plus 1, and they want you to find the code word. Okay, what is the code word? Okay, so let me show you the idea how we will do it. So one way that is very easy is you convert this data word to binary. So 1, then 0, the x power 1, x power 2, x power 3. So 1001. Are you getting it? See this, x cube plus 1 now, so 1 1 as it is. So now x power 1 is 0. Okay, x power 2 is 0, x power 3 is 1. So I have written like this. Please let me know if anybody is having any doubt here. Okay, and let me solve one more. See how we will write it, x cube plus x plus 1, 1 as it is, then x power 1 is 1, so I will write it here 1, x power 2 is 0, x power 3 is 1, so 1011 is the divisor. Okay, so how you will find the code word? I think we have already studied this type of questions, so we can do it easily, and then whatever we will get, we will give the polynomial notation. For example, 1011, then 1001. Okay, and the divisor is of 4 bits, so I will add 3 zeros here, and then I will do modulo 2 division 1011. So here cross 1000. Okay, so I will say 1011, and here 11 cross, and here 0. So final answer will be 1001,110. So you will convert it into polynomial, x power 0, x power 1, x power 2, x power 3, 4, 5 and 6. So finally x power 6 plus x cube plus x square plus x. This is my answer. Okay, x power 6 plus x cube plus x square plus x. So I hope you have got the point. So let me write it more clearly. This was x power 6, x power 0, x power 1, x power 2, x power 3. Okay, so finally polynomial is this. So this is my final answer for the code word. But why we want to do like this? It is a bit lengthier method. So let me show you a shortcut method or direct division. How you will do the direct method. Okay, so let me show you the direct method. So what is the direct method? So data word is this. Divisor degree is, I think you already know, this is polynomial. Polynomial degree is highest power, so x cube. So you multiply this by x cube. What you will get? X power 6 plus x cube. And this is nothing but your this. Okay. Now divisor was x cube plus x plus 1. So now you will try to divide it. So what we will say, x cube and x6. So x cube you will take, we will get x6 plus x power 4 plus x cube. Now here quotient writing is a bit, you can say it is not compulsory, but I will suggest you that you write here quotient. Why? Because if you write here quotient, then multiplication will be very easy for you. Everything will be in front of your eyes and you will be able to solve quotient very easily. So x cube into x cube, that will be x power 6. X cube into x, that is x power 4. X cube into 1, that is x cube. So now what we will say, we will simply you can say cross the common terms. Okay, finally we have got x power 4. Okay, so this is like this only. I'm not going into details that how exactly we are doing these things, because it will unnecessarily waste our time. So basic mechanism I'm just showing you. So we will get x4. Now do not say, sir, here should be minus and all, because it is modulo to division. Okay, it is not your actual division. And just because modulo to division XOR operation we are doing, so XOR means x power 6, and here also x power 6. So same place 1 means it will be cut down. Okay, x cube, same place 1, it will be cut down. X4 is here, x power 4 is not here, so here it will be 0, here it will be 1, so you have added, so you will get x power 4 here. Okay, yeah, finally x cube is here, x power 4 is here, so yeah, I have to I will say x, and then I will do you can say division. Okay, yeah, so what finally I will get, x power 4 plus x square plus x, so this will be cut down, x square plus x. So now here we have x cube and here we have x square, so stop it. So what will be our final answer? See, we have added this and remainder was added, so you simply add them. So what you will get, x power 6 plus x cube plus x square plus x. This is my final answer, and this is same as what we have shown you. Please let me know if anybody is having any doubt. It was very intuitive method. If somebody wants me to explain again, I will explain again. No need to worry. Please let me know.
Good evening, sir. So I
Yeah.
understood the procedure, but one thing I missed out understanding, like how did we make the dividend?
Okay, this thing, no, it is easy. So divisor degree was x cube. So you will multiply data word by x cube itself.
Okay, sir.
And why we are multiplying? Because x cube means power 3, na? So here we were adding 3 zeros. That's why we have multiplied it.
Yes, sir. Done, sir.
Okay. Yeah. Any other doubt?
No, sir.
Okay. Please. Any? Yeah.
I want you to explain this just again.
Please come again.
I want you to explain this very quickly again. Just.
Okay. Again. No problem. See this. Data word and divisor. Data word is x cube plus 1, and divisor was this. So I have take divisor degree was 3 x cube. So data word will be multiplied by x cube, but we will get x power 6 x power 3 x power 6 x power 3 we have written. So divisor was x cube plus x plus 1. Here I have written it. So x cube and x6. So x cube I have to write here, na? So x cube into x cube, x power 6, x cube into x power 4, x cube into 1, x cube only. So x6, x3 gone. Why they are gone? Because imagine x6 means 7th place 1. See, x power 0, x power 1, x power 2 dot dot dot, x power 6. So x power 6 means 7th place 1. And here also we have 7th place 1. So 1 and 1 XOR means it will be gone. So that's why I have simply cut down. X power 6 cut down, x6 cut down. Finally x4 was remaining, so I have written here x4. Now x4, here we have 4, here we have 3, so obviously I can divide it. So finally I have written here x, then x into x cube, it will be x power 4, and because of x, and here x square, because of x, here 1, so x. So x4 cancelled out, x square plus 1 is remainder, and x square, and here we have x cube. So I will say no, I cannot do further division, so game over. So finally remainder is x cube plus x, sorry, x square plus x is the remainder. So initially what we have done in binary, so whatever was our divisor, we add the remainder. So here also we will add the remainder. So x6 x cube, and then I will add x square plus x. This is what we have got. From binary also the same was same we have got. Is it okay?
Okay, sir.
Okay. Take snapshot. I will jump to the next slide, and I will solve another question.
Done, sir.
Done? Okay. Yeah. So for example, I can say divisor is x square plus x plus 1. Data word is x power 4 plus x square plus 1, and we want to find the code word. So divisor is x square plus x plus 1. Okay, and data word is x power 4 x square plus 1, and what is the degree here? X square. So I will multiply this entire term by x square, x power 6 plus x power 4 plus x square. So now I will start doing division. So x power 4 will be here, 4 2 x power 6 plus x power 5 plus x power 4. 6 and 6 gone, 4 and 4 gone, x power 5 plus x square. X square was here now, so I will take it down. X power 5 plus x square we have, so then plus x power 3. So what we will get, x power 5 then plus x power 4 then x power 3. 5 gone. Finally what we will get, x power 4 plus x cube plus x square. So then I will say x square. X square into x square, x power 4. Why I have not stopped? Because here we have 4, here we have 2. So I have to carry it again. So x power 4 plus x power cube plus x square. So what we will get? Gone, gone, gone. Nothing is left out. No problem. So finally our code word will be x power 6 plus x4 plus x square. That's it. This is my code word which will be sent. Any doubt?
So once again the dividend only. X power 4 multiplied with like x power 2 and then x power 4, and how did we get x power 2? So
no. X power 4 plus x square plus 1, you simply multiplied by x power 2. So x power 2 into x power 4, x power 6.
Highest degree was x power 4, no sir? Why do we multiply it with?
No, divisor degree, divisor.
Last time
we are
also,
not checking data word.
हाँ sir. Last time divisor नीचे लिखा था मैंने.
Okay. Acha, okay. yeah. So I have swapped that thing.
Attempted before you wanted to do it.
Okay. Yeah. So please take snapshot. I will jump to the next slide.
Done, sir.
Okay. So now you might think that how this divisor is chosen, because this divisor should be known to sender as well as receiver. Divisor. Okay. Let me do it on the fresh slide. Take snapshot. I will jump to the next slide.
Done, sir.
Done. Okay. So now question arises, how these divisors are chosen. How these divisors are chosen. Okay, so for that we have a big theory and we are not digging into deep because it is not required for gate. But the only thing is that this divisor must be known to sender as well as receiver, because they both have to do the division, na? So divisor must be known to sender as well as receiver. Okay, because both will do division. Both will do modulo 2 division. Okay, so it must be known to both. So for example, I will tell you a little bit idea. CRC32. Okay, so CR32 means 32-bit divisor we are taking. Real life scenario I am explaining you. Okay, practically what in computer networks what we are doing. So we are taking 32-bit divisor. Okay, 32-bit divisor is very huge. CRC32, and it is used in Ethernet LAN. So when Ethernet protocol, we will study Ethernet protocol, don't worry about it. So in Ethernet protocol, we will use CRC32. This question has been asked in gate. That's why I have explained you. So how many bits divisor will be chosen for Ethernet? It will be 32-bit divisor. Okay. Yeah, and how exactly it look like? It hardly matters to me. Like x power 32 plus x power 30 plus x power 19 plus x power 16 ... something it will be there. It hardly matters to me. I'm just showing you the idea. Okay, and this is standard divisor what we are choosing. So no need to worry. Both sender and receiver know this divisor at start only. Okay, so they need not exchange this divisor and all. Like sender will not say to receiver that this is my divisor, you have to divide it by this number and so on. Why they are not exchanging? Because error might occur in divisor also. So if received divisor is wrong, then obviously everything will be wrong. So better is to take the standard divisors only. Okay, so CRC32 is used in Ethernet. Yeah, take snapshot. I will jump to the next slide. Now our CRC scheme is over. Now we are going to start the last error detecting scheme, that is checksum. Okay. So now we are going to start the last scheme, that is checksum. Okay, so checksum is also based on concept of redundancy. It is also based on concept of redundancy. In fact, every error detection correction scheme is based on concept of redundancy. That is, redundancy means adding some extra bits. Adding some extra bits. Okay, that is redundancy or redundant bits. Okay, so another important point is no protocol at data link layer. We will study many protocols, don't worry, but none of the protocol is using checksum as error detection scheme as data link layer. Okay, no protocol at data link layer is using checksum for error detection. Okay, so why we are studying it? We are at data link layer. I have told you we will study layer by layer. First we have completed physical layer, now we are studying data link layer and so on. But why I am explaining it here? Because we are studying error detection correction scheme only, and my aim is to complete this topic here itself. That's why I am just explaining it here. Okay, but it is used at higher layers. So no protocol at data link layer is using error checksum for error detection, but it is used at higher layer. But it is used at higher layers. Okay, for example, TCP at transport layer is using checksum. TCP at transport layer is using checksum, and even IP is also using checksum. So now you may argue with me, sir, you have told that IP is a best effort delivery system. There is no error detection mechanism in IP, but now I am saying that IP is using checksum. So IP is using checksum for its header only. Okay, actually a network layer is adding header now. Every layer is adding header. So network layer is also adding header. So IP is using checksum for this header only. Okay, for data it is not doing any error detection correction scheme. Okay, so that's why you should know IP is using checksum. These are very, very important points. Okay, you have to understand them, or you have to learn them. IP is using checksum and it is for header only. TCP is also using checksum at transport layer, and it is for header as well as data. Okay, so you use that higher layer. TCP at transport layer is using it, and it is for header as well as data. Okay, but IP is using checksum for header only. Okay, and what exactly is checksum? Don't worry, now I am going to explain it. Take snapshot. I will jump to the next slide, and now I will explain you this topic, what exactly is checksum. And you have to remember this: no protocol at data link layer is using checksum. Okay, higher layers are using. Take snapshot. I will jump to the next slide. Done? Okay. So the next is I have to explain this. So for example, sender wants to send few numbers like 7, 11, 12, 0 and 6. So how many numbers are there? Say 5 numbers. So sender wants to send these 5 numbers to the receiver. So now what it will do, so how error detection or correction will be done? Rather error detection, forget about correction, how error detection will be done. So obviously we have to add some redundant bits. So as the name suggests, check sum. That means you have to check the sum. So what you will do, you will sum them up. So 7 plus 11 plus 12, 0 and 6, it comes out to be 36. You can check that out. 7 plus 11 plus 12 plus 6, 36. So in place of sending only data, you are sending its sum. Okay, sum of data. Are you getting it? So this we are doing. So now finally this will be sent to the receiver, and at receiver side what it will do, it will add all this. It will get, okay, answer is 36, and here also we have 36, so they are matching. Okay, but this is the rough way. What exactly is done, let me show you that. So in place of sending 36, it will send minus 36. Now what will be the advantage? So now receiver does not has to select that first few numbers we have to select, last number we have to you can say not select and add and so on. It will simply leave all those things. It will simply add all these numbers. So result should be 0. If result is coming to be 0, it will say okay, accepted. And this is exactly checksum is. Okay, and now but still we have a very small problem here. What is the problem? 7 is represented in only 3 bits. 11 represented in 4 bits, 12 in 4 bits. Do you know these things? Na? 11 is 1011, 12 is 1100. 0 only, rather we will say only 1 bit is required to represent 0, that is 0 itself. For 6 we need 3 bits. So entire data needs only 4 bits. But how you will represent 36? 36 is 100, 100, 6 bits. So that is creating problem in our mind that data itself is of 3 or 4 bits or sometimes 1 bit. Why we are sending this sum of 6 bits? That will create problem. And these are very small numbers. Practically we are not sending 5 numbers. We will send 50,000 numbers. Okay, so why we are sending these numbers? Because we want to do some data analytics and so on, like we want to sort the numbers. So if you want to sort the number and you have only 10 numbers, why you will write merge sort or quick sort program in your computer? Why you will type that? Why you will compile that? Why you will do that? You can do on your pen paper also. So for 10-20 numbers you can do it on your with pen papers also. You do not need computer. We need computer if we want, say I want to sort 10,000 numbers or 50,000 numbers. Okay, so asymptotic analysis and so on, you have studied that in algorithm. Okay, so the basic scenario is real life we want to send very huge numbers. Okay, so if we are sending very large numbers, say 10,000 numbers and all, their sum will be very, very large, and that will create problem for us. So now we will modify the scheme a little bit. What we will say, we are sending 4-byte data, that is maximum. So we will try to send 4-bit data as a sum. So how we will do it? We will do folding method. What is folding method? 100, 100 was there. So I will apply here. You can say I will. You can say I will cut this. Okay, here itself. So 0 1 0 1 0 0 is there, and I will add this 1 0 here. So 0 1 0 and 1 0 I will add. 1 0 I will add. Finally we will get 0 1 1 0. This is 6. So now in place of sending 6, what I will send, because negative numbers are sent now, so for negative numbers we will use 1's complement here. 1's complement means we will make 1 to 0, 0 to 1. Finally what we will get 9. Okay, so in place of sending minus 36, I will send here 9. So finally what I will get, please see this. What I will get? I will get 7, 11, 12, 0, 6 and 9. This thing I am sending to the receiver. Receiver, after receiving it, it will simply add it. So till this we have already added 36. 36 plus 9 is 45. So 45, it will count the sum. Total sums counted by receiver will be 45. What is the binary of 45? 1 0 1 1. 11 11 followed by 0 is 22, 22 and then 1 we will get 45. I think this is a simple shortcut to find the binary. So let me show you that. So see this 101, it is 5. I think you already know. If I add here 0, it will become 1010. That means 10. Okay. If I add again 10 here, so it will become 20. You can check that out. So if in binary number I append 0, that means we are multiplying by 2.
Yes, sir.
Yeah, adding 1 means multiply by 2 plus 1. In TOC and all, I have told you these shortcuts. 0 means multiply by 2, 1 means multiply by 2 plus 1. So that's how I have written very fastly 101 1101. That is 45. Okay, this is the 45. So now what I will do, 101101, I will cut it and I will place it here. But I will get 110110. So what we will get, 4 times 1. Now I will do 1's complement. Okay, 1's complement will be all zeros. So finally, since we have got zeros, so it will be accepted. Like this we will do. Okay, so if anybody is having any doubt, please let me know. I will try to explain it again.
So after folding, we once complemented it. 45.
Yeah.
Again, we appended from 45 onwards, sir.
Okay, 45 onwards. Okay, so yeah, this was 45 binary. So I have written here 45. I will folding method now. So 10 I will add it here. So I will get 4 1's. So what we have to do, 1's complement, negative numbers 1's complement we are doing. So I will again do its 1's complement, and finally what I am getting is all zeros. So it will be accepted.
It
Okay,
means
so
that this is
basically
happening at the receiver end.
Yeah. These all things are happening at receiver end only. Yes. So I have told you now that 45 at sender has sent all these numbers, and receiver will sum them up. After summing them up, receiver has got 45. So what is 45? I have written here. So folding method applied and all ones, and we will do ones complement, and final answer is all zeros. That's it.
Sender is also applying folding method and receiver is also applying.
Yes, 100%. Because if one apply, one does not apply, then obviously scheme will not work, na?
Okay, here in the senders, like as the minus sign is included, it doesn't change the binary representation of it. Minus
30. I'm just assuming that. That 1001 is 9.
You not to mention minus 36 there because it is not 36 anymore. It is like 9.
Yeah, it is 9. That's why I have represented here 9.
Sir. Understood.
Okay, and here we have done ones complement now. So here also we have to do ones complement.
Yes, sir. Yes, sir.
So that's why I'm getting all zeros.
Things should be 0. Sir.
Okay. Yes. Please, anybody is having any doubt, please let me know. Otherwise, I will jump to the next slide. This is all about checksum. And anyway, these things are not that much important. The basic thing is you should know what is checksum. Checksum is an error detection scheme, and it is used by these questions have been asked. Okay, IP for header only, for TCP header plus data. These type of question has been asked. So I have just given you these details that how we are adding and so on. Okay. Yeah. So you can take snapshot. I will jump to the next slide.
Done, sir.
Okay. So do you think that this scheme is perfect? Like in CRC we have done, it was not coming to be perfect, but probability of getting those errors were very, very less. So same is the scenario here. Is this perfect scheme? Clearly no. Why? For example, what was the data? 7-11-12-06. 7-11-12-0 and 6. You forget about everything. I simply say here 1 subtracted and here 1 added, or you can say here 1 subtracted and here 1 added. So what you will get? 10, 13, 0 and 6. What was the sum here? 36. Here also 36. Scheme failed. Okay, so 1 bit error occurred here also and here also. So last bit of 111 is 1011. So this one was changed to 0. Okay, so you have got this. And here in the 12 last bit become 1. So we will get like this. So that's why I've written 13. Okay, so here 1 subtracted and here 1 added. So obviously that is creating problem. So it is obviously not perfect scheme. And as for such errors, we can see that probability is very high. Okay, because last bit of every data is affected and so on. We can think like that. So it might create problem. That's why it is not perfect scheme. Okay, so CRC is much better than your checksum. CRC is much better than your checksum. And another very big disadvantage of checksum, let me show you that also. Okay, so another big disadvantage is, for example, if you want to, you can say send large amount of data. Okay, and say I am saying that checksum is of 16 bits. Okay, so they will directly say 16-bit checksum is used, and generally 16-bit is used only. Okay, 16-bit checksum is used. They will say like this, and data is very large. So what you will do? So this is your data. You have to divide it into 16 bits chunk, and then you have to add these chunks. After adding, you will get a very big binary number, and you will do folding method and all. Isn't it lengthy? It will get very big problem. Are you getting it? So practically we are sending very huge amount of data. For example, you are sending 2 power 16 bits data. Okay, or rather 2 power 16 bytes. Generally 2 power 16 byte data is sent. Okay, so packet size is generally 2 power 16 byte, and here we are saying 16-bit checksum. Okay, so byte will be converted to bit. So 2 power 19 bits. Are you getting it? 2 power 16 byte. So byte means into 8 we will do. Into 8 means 2 power 3. So 2 power 16 into 2 power 3, that will be 2 power 19 bits. 2 power 19 bit data, and 16 bits you are taking. So 2 power 19 divided by 2 power 4. 16 is 2 power 4. No need to divide and all. So we will study these things in IP addressing also. Okay, so how you will divide 2 power 19 by 16? No need to do this kind of thing. You simply make power of 2. 2 power 19 divided by 2 power 4. It comes out to be 2 power 15. 2 power 15 is very huge number. 2 power 15 is 32768. 32,768 parts you are making, and 32,768 parts you are adding, and finally whatever you are getting a very huge number, you are doing folding and then you are adding. It will simply wastage of time. That is another very big disadvantage of checksum. Okay, so one big disadvantage is one added, one subtracted, and so on. And another disadvantage, that means it is not perfect scheme. This is one of the disadvantage. And second disadvantage is you can say it is very time consuming. Okay, so let me summarize it. So first disadvantage is it is not perfect scheme. That is for sure. Second is time consuming. Time consuming. Okay, yeah. You can take snapshot. I will jump to the next slide.
Okay.
Done. Okay. Yes. So now what we will say in our data link layer, our one of the major topic has been completed, that is error detection and correction, and I have shown you many techniques also. Hemming codes was very important because it was error correcting code, and only one error correcting code is in your syllabus, that is Hemming code. Many times question has been asked. Very important scheme. Okay, CRC scheme is also very important. Okay, used for error detection only. Okay, and many times question have been asked. And another scheme was a simple parity check code. Simple parity check code, SPCC. It is again error detection scheme. Okay, so sometimes question have been asked. It is not so important, but these two are very important, Hemming code and CRC. Okay, so now this is all about your error detection. So I have told you data link layer is receiving packet from the network layer. Packet of network layer is datagram. So to this datagram, it will add header, it will add trailer. This resulting structure is known as frame. You have to remember wording. Data link layer, packet name is frame. Network layer, packet name is datagram, and so on. I have told you many times. Okay, so this is the frame. Trailer, I have told you, it is used for error detection and correction type of thing. So we have studied that. So now we will study the header part. So what exactly header contain? So, or rather what exactly header is doing, or you can say functionality. So it is basically doing three things: flow control, error control, and access control. Error detection is done here. Error control means different thing. I will tell you, don't worry. Error control, you can simply think that packet is lost, what to do. Okay, that thing cannot be done by trailer. Trailer is just doing error detection. Like receiver has received the packet, so is it correct or not? That can be done. That is error detection. Error control is a vast term. Error control means if frame is lost, what to do, if acknowledgement is lost, what to do, and so on. This kind of thing we will study here. Okay, so header is doing these three things: flow control, error control, and access control. Okay, so let me show you that. And one more thing it is doing: framing. Framing also. Okay, framing means okay, so this is not done by header. Sorry for that. Yeah, so these three things are is the, you can say, main aim of adding the header. It is doing flow control, it is doing error control, it is doing access control also. Don't worry, we will study these things. Okay, but first thing is you have to study this frame also. Okay, how this framing is done. A very basic question will come to our mind: how this framing is done. Okay, so let me show you that how this framing is done. Take snapshot. I will jump to the next slide.
That's all.
Okay, so sometimes 1 or 2 times question have been asked from framing also, so you have to study it properly. Framing. So how framing is done? Okay, that is the basic aim of your data link layer, because it is adding header and trailer and making the frame. Okay, so actually frames are of 2 types. First of all, you should know these things. Frames are of 2 types. One is known as fixed length frame. Fixed length frame, and another is known as variable length frames. Variable length frames. Okay, so fixed length frame means size of frame is always fixed. Okay, and that is generally used in ATM networks, and this is not in your gate syllabus, so we will not study that. We will study variable length frame. Variable length frame means obviously frame size is variable. Sometimes you are sending say 500 byte frame. Sometimes you are sending 10 say 1000 byte frame. Sometimes you are sending 2005 byte frame, and so on. So variable length frame means size of frame is variable. Okay, so it is generally used in your Ethernet protocol, and Ethernet we have to study in detail. Don't worry about it. Okay, after 1 or 2 classes we will study this protocol. So Ethernet is using variable length frame. These types of question have been asked repeatedly in gate. What Ethernet is using, fixed length frame or variable length frame? It is using variable length frame. Okay, so now they will ask you what is the minimum size of frame, what is the maximum size of frame, and so on. Don't worry, when we will start Ethernet I will tell you all these things. Frame size, this question has been asked many times in Match the Following. Okay, or sometime directly, sometime indirectly, and so on. So Ethernet smallest size frame or largest size frame, all these things you should know properly, and don't worry, we will study that when we will start the Ethernet protocol. Okay, so the basic idea is it is using variable length frames. Now let me okay, take snapshot. I will jump to the next slide. Done. Okay, so now since we have variable length frame, so how it will look like? So we will have an header, and here we will have variable length of data, variable length data. Now do not say header will change and so on. Header is fixed. Similarly trailer is also fixed. Okay, do not say that header and trailer are of variable size. No, header and trailer are of fixed size. We will have a variable length data. Okay, or you can say datagram length will be variable. Okay, sometimes datagram will be of big size, sometimes small size, and so on. That is the basic scenario. Okay, now directly indirectly I want to say that this entire structure, this entire frame, this length is not fixed. Okay, length is variable. Why length is variable? Because header is fixed, trailer is also fixed, but this is variable. So overall this entire frame become variable. So now since it is of variable length, so sender is sending it and receiver will receive it. So how receiver will come to know that here frame ends, or how receiver will come to know that here frame start? So directly indirectly receiver will not be able to guess the frame boundaries. That is the biggest problem. So for variable length frame, what is the biggest problem? Receiver will not be able to guess. Receiver will not be able to guess the frame boundaries. Okay, where frame start, where frame ends, and so on. So for that we will add a special byte of data called flag. Okay, at start also and at end also. So flag is 1 byte of you can say data. Okay, so which will represent start of frame and it will represent end of frame also. So at start and end of frame we will apply flag. Okay, and what is flag? Flag is 1 byte. Okay, 1 byte data, or data will confuse you that this is also data, na? So you simply say flag is of 1 byte. Okay, so this flag and this flag, they are exactly same, no problem, and their size is 1 byte. 1 byte size you can write. Okay, 1 byte size. Okay, so I hope you have got the point. So flag at start and flag at the end. Okay, and this is 1 byte size. Okay, and why we are adding it? Because receiver will not be able to guess the frame boundaries. Okay, so now question arises that how this flag will look like and so on. So for that, let me show you the idea. Take snapshot. I will jump to the next slide.
Okay,
Done?
so.
Okay, yeah. So actually we have two approaches. We have two approaches. First approach is character oriented approach. Character oriented approach. And second is bit oriented approach. Bit oriented approach. So for character oriented approach, flag is not fixed. Flag is not fixed. You can take any byte of data, whatever way you want. You can take like 101, 101, and so on. Whatever way you want, you can take. It is not fixed. Okay. So for character oriented approach, flag is not fixed. Okay. So as the name suggests, character oriented. So character is generally of 1 byte. Okay. So you can say that your frame itself will be multiple of you can say 8 bits. Okay. 1 byte is 8 bits. So you will say your entire frame will be multiple of 8 bits. Okay. So character oriented approach means entire frame will be multiple of 8 bits. Multiple of 8 bits. Okay. And that means flag is of 1 byte, that is for sure. Your header, trailer, datagram, everything. Okay. Or you can say data, header, trailer, data. So everything will be multiple of 8 bits. That is what character oriented approach is suggesting. And one more thing it is saying that you might face a problem that this is header and this is say data and this is trailer. What if this data itself contain the flag? Nobody is stopping us to put flag here also. Flag is a 1 byte of 1 byte, na? So this combination might appear in data also. That will create problem. So for that, what they have suggested is we will add a special character. We will add a special character called escape character. Escape character. Okay. So this escape character is used, say as the name suggests, escape from special meaning. Okay. Escape character means escape from special meaning. Escape from special meaning. Okay. So if flag appears in data, then before flag we will add escape character. That is again a special character. Okay. Forget about how it's look like and so on. It entirely depends on your programming way and all. Okay. So the basic thing is that if flag appears in data, so before flag we will add escape character, and it means escape from the special meaning. So everything will remain fit and fine. So I have addressed a very simple problem. That what was the problem? If flag appear in data, flag appear in data, what we have to do? So before flag add escape character. Before flag add escape character. So basically what we will send, escape flag, like this. So if this comes, then this flag is in your data itself. It is no longer a special character. So I hope you have got the point. Now another problem is that you might say, sir, escape character is also a special character only. So it is also sequence of some bits like this. Okay. So now since it is also sequence, so it might also appear in data. So first problem was flag appear in data. So before flag add escape character. So escape flag we will send. Second is if escape appears in data. Escape appear in data. No problem. You will send escape 2 times. So this escape means escape from special meaning, and this escape means this will treat it as data itself. Okay. So now if escape flag both appears in data like this only. So what you will send? So you will send escape and then you will send this escape. Okay. And then for this flag you will send escape and then you will send flag. So this escape will be ignored by receiver. This escape will be accepted as data. This escape will be ignored by receiver and this flag will be accepted as data. So I hope you have got the point. So this is your character oriented approach. Any doubt here? Yes, please let me know if somebody is having any doubt.
No, sir, understood, sir.
Okay, so it was very easy. Okay, so there was nothing so much technical here. So I think everybody have got the point. Okay, so the next thing is that, or you can say another name of character-oriented approaches, or rather what we are doing here. Let me say it here itself. Okay, so if flag appear as data, we are putting escape character, na? Escape character is 1 byte of data, na? So what you are doing, you are adding 1 byte of data to your data. Whatever data you were sending, you are adding 1 extra byte to it, or you are stuffing that byte in your data. That's why we call it as byte stuffing. Okay, so this approach is known as byte stuffing. So byte stuffing means add escape character, add ESC if flag appears, if flag comes in data. Okay, that is byte stuffing. Or you can say simply, you can say character oriented approach. This I was explaining you, this entire thing was character oriented approach only. So you can call this as byte stuffing also. Character oriented approach or byte stuffing, one and the same thing. Okay, and what exactly byte stuffing means, we will add escape if flag comes in data. So this escape is nothing but your 1 byte of data which you have stuffed into your data. That's why we are calling it as byte stuffing. Yes, please let me know if anybody is having any doubt here. Yes, any doubt?
No, sir. Clear, sir.
Okay. So next is bit oriented approach. So we will call it as the name says, bit oriented approach means bit stuffing. Bit stuffing. So what is bit stuffing? Let me tell you that. I will jump to the next slide. Please take snapshot. Done?
Done, sir.
Okay. So now we are going to start bit stuffing or bit oriented approach, one and the same thing. Character oriented approach or byte stuffing, one and the same thing. And why we are calling it as byte stuffing? Just because we are adding extra character, or you can say we are stuffing this escape character if flag comes as data. Okay, yeah. So what is bit stuffing? Bit stuffing means, so here flag is fixed. Flag will be 0, 1, 2, 3, 4, 5, 6 and here 0. Okay, this is your flag. Why this flag is chosen? Don't worry, I will tell you about it. Don't worry. So first of all, I am just giving you the idea. Flag is fixed. For bit stuffing, that is this. Now, if this flag appears as data, that was the biggest problem, na? So here also I have explained you this way only. Character oriented approach, frame will be multiple of 8 bits and so on, but here there is no need of that frame should be multiple of 8 bit and all, because we are doing bit stuffing. So no need that the frame is a multiple of 8 bits. So frame may or may not be multiple of 8 bits. Frame may or may not be multiple of 8 bits. Okay, yeah. And flag was fixed. Okay, what was the flag? Flag is 0 followed by 6 ones and then 0. Okay, so now again I will discuss the same problem. What was the first problem? If flag appear as data. Flag as data. So as the name suggests, bit stuffing. So what we will do? So this is our rule. Whether flag is coming or not, I will say after 0, 1, 2, 3, 4, 5. There are 6 ones now. So after 0, we will get 5 ones. I will append 1 0 by myself. Okay, and then I will add 1 and 0 and so on like this. So after 5 ones, we are adding 0, or sender is adding this 0, and this 0 will be ignored by your receiver. Okay, so sender is putting this 0, sender put this 0, if flag as data is coming, because what is flag? 0 followed by 6 ones and then 0, that is the flag. So problem is after 0 6 ones should not come. So I have simply said that after 0 6 ones should not come, so after 0 5 ones can come. So after 0 5 ones can come, and immediately after 5 ones we will add 0. This 0 will be stuffed by sender. That's why we are calling it as bit stuffing. Only one bit has been stuffed. So this 0 will be stuffed by sender and it will be ignored by receiver. Ignored by receiver. So if sender has sent this sequence, what receiver will receive? Receiver will say 0, 1, 2, 3, 4, 5. This 0 will be ignored, then 1, and then this 0. So this flag now successfully appears as data. No problem at all. Okay. Now this flag is successfully flag successfully appears as data. So I think there is no problem. Okay, so flag appears as data, problem is solved. Now escape appears as data and so on. So escape is not here. So we will not address this problem. So one problem was there, that flag appears as data. We have solved that. Now another problem, another big problem you can think of is, if after 5 zeros, a 1 0 is already there in the data. What if after 5 ones we have 0 in data? Then it is common sense. What we will say, after 0, 1, 2, 3, 4, 5 ones, and then 0 is in your data, no problem, you add 0. Okay, and then again you will add 0. So now this 0 will be ignored and this 0 will be accepted. So for example, if I say like this is my, you can say, if sender has sent this. Okay, so sender has sent this data. So how receiver will receive it? No problem. So how receiver will receive it? It will say 0, 1, 2, 3, 4, 5. This 0 will be ignored, and then 2 zeros and 2 1. This will be accepted. Okay, so what if after 5 ones we have 0? No problem. So before the 0 we will add one more 0. So that is rule, that is simple rule. Whether it is flag or whether it is not flag and so on, after 5 ones we will add 1 0. And this 0 will be added by sender and it will be ignored by receiver. That is for sure. Okay, after that, whether we have this, we have 1 here, so we can have 0 here also, it will be accepted, no problem. Whether we have 1, whether we have 0, no problem, it will be simply received by receiver. So after 5 1, adding 0 is compulsory by sender in data part. Okay, if we are sending flag, then obviously it will not add 0. Okay, but if it is sending data, then in data after 5 ones it has to add 0. Okay, so sender has to add 0 and this 0 will be ignored by receiver. Okay, so let me solve one gate question. That was very simple. I am not writing entire question just to save the time. So this question has been asked in gate 2015. So what was the question? They have simply said, they have given you a very big theory and all. I am not writing that theory because I have explained you all the things. I am simply giving you the question. 0 1 2 3 4 5 0 0 1 0 1. This was sent by sender. So what receiver will receive? 0 1 2 3 4 5. This 0 will be ignored. Then 0 1 0 1. This will be received by receiver. That's it. Okay, so 1 0 is ignored. That's it. I think I have got you have got the point. If somebody is facing any difficulty, please let me know. I will try to explain it again. Otherwise, we will jump to the next slide.
Understood, sir.
Okay, take snapshot. I will jump to the next slide.
Answer.
Okay. Yeah. So next is this is all about framing. Framing we have done. So where were we? Yeah, so framing, how these frame are made, we have completed. So now we are jumping to this flow and error control. After studying flow and error control, we will start the access control mechanisms. Access control are very, very important. I think you have heard the word CSMA, CSMA CD, Aloha, slotted Aloha, and so on. They are very, very important. Many times question has been asked, and these are also very, very important. Flow control and error control. Many gate questions are there. Okay, many numericals are there. Okay, don't worry, we will study that one by one. So these now the two topics which we are going to study are very, very important for data link layer. Okay, so one question will definitely come in your gate exam related to flow and error control or related to access control. One question definitely come. So these are very important. So you have to pay full attention here to understand these topics. Okay, otherwise you might face some difficulty. So one topic is flow and error control, second is access control. Both are very important. Okay, so we are going to start flow and error control. Okay, so I have told you in the previous lectures also what is flow control. Receiver should not get overwhelmed. Sender should not send at us at a very high speed, and if sender is sending at a very high speed, receiver is not able to receive at that much speed, then obviously receiver will be overwhelmed. Everything will go above its head. That will create problems. So this situation must not arise. Okay, so receiver must never be overwhelmed. So how this receiver will never be overwhelmed? Because we have flow control mechanisms. Okay, so what is flow control? Flow control, I have told you the technical definition, that is amount of data that can be sent, before receiving acknowledgement. Amount of data that can be sent before receiving acknowledgement. Okay, so how much amount of data sender can send before receiving acknowledgement from receiver? Okay, that is the basic meaning of flow control. I hope you have got the point. Okay, I have given you real life examples also, like I keep on speaking at a very high speed and all, so you might get overwhelmed. So after speaking few lines, I will stop and I will observe you, or I will wait. That I will say somebody is having any doubt and or so on. If you give me acknowledgement that everything is okay, then I will speak again and so on. Okay, so this entirely depends on me, that how much lines I am speaking. Okay, so I should get a feeling that you might not get overwhelmed. So after speaking few lines, I am stopping myself, and then you are giving me some idea that okay, we have got it, and then again I am repeating. Okay, so that is the basic meaning of flow control. So I am controlling the flow. Okay, if I do not do flow control, then obviously most of you will be overwhelmed, because I will keep on speaking and so on. That will create problem. Okay, yeah, so flow control means amount of data that can be sent before receiving acknowledgement. Okay, that is the flow control. Okay, so how error control is done? That means if say frame, okay, frame lost, or ACK is lost, or frame is corrupted, and so on, that is error control. Okay, so error detection means this only, that frame corrupted, you have to check that out. Okay, so receiver has received the frame, and now it will apply error detection and so on to check whether the frame was correct or not. That was error detection. Error control is big term. Error control means you have to control all the errors, like frame lost, acknowledgement lost, frame corrupted, and so on. You have to check all these. That is error control. Okay, so whatever may be the case. Okay, for example, take this scenario, frame corrupted. So what do you think? Sender has sent the frame to receiver. Receiver received the frame and it is saying no, frame is corrupted. So what should receiver do? Receiver should send NAK that no, your frame is not correct, please send it again and so on. No, it will not do that. We can do that, no problem in that, but it will unnecessarily increase the load in your network. Many NAKs will keep on running in your network and so on, and the network there might be some congestion. So it's better that receiver should not send NAKs and so on. Okay, it is much better that receiver should not send these NAKs. So what it will do? Of course, there are some protocols where NAKs are sent. Don't worry, we will study that also. But for now, you should imagine that if sender has sent some data, receiver has received it, and after applying error detection mechanism, it came to know that frame is corrupted. So what receiver should do? Receiver should say, or receiver should send NAK to sender? No, because it will unnecessarily increase the traffic in the network. So what is the better way? It will silently discard the frame. Okay, so it will not send NAK. Okay, so frame is corrupted, so it will not send NAK. It will silently discard the frame. Silently discard. That means it will not send anything to the sender. Silently discard the frame. Okay, so you can think like that. Receiver, or you can say the receiver is very sensible person. Okay, if somebody is talking wrong, he will not say no, you are telling wrong and so on. And he will not fight with him. He will stop saying something. Okay, he will stop responding. So someday or other he will stop sending wrong things and so on. Okay, are you getting it? So receiver is very sensible person. He's not saying sender that you are wrong and so on. Okay, he himself keep quiet. Okay, and sender will come to know, okay, something I think I have spoken wrong, so I should not speak those words in front of you and so on. That is the best way to deal the things. Okay, that is done by receiver itself. So it will silently discard the frame. Okay, so now question arises, how sender come to know that receiver has not received the frame? So obviously receiver will not send ACK to the sender. If receiver is sending ACK, that means acknowledgement to the sender, then sender will come to know that okay, receiver has received the frame properly. But here receiver has silently discarded the frame, so receiver will not send ACK to the sender. Okay, so now you might think that sender is waiting for the acknowledgement from the receiver, that when acknowledgement will come, sender will say okay, I will send the next frame and so on. And receiver is waiting for the sender that since I have silently discarded the frame, so now receiver is expecting that sender will send the frame again and so on. Are you getting it? So receiver is dependent on sender and sender is dependent on receiver. Why receiver is dependent on sender? Because receiver will say that I have silently discarded the frame, so sender should send it again. But sender is not sending. Why? Because sender itself is dependent on receiver. Because sender will say once acknowledgement come, then I will send. Okay, so are you getting it? So there we will have a loop. Sender is waiting for receiver, that receiver will send ACK, I will send the frame again. Receiver is waiting for sender because it will say that I have silently discarded the frame, so sender will send it again. So clearly this is deadlock. It is a deadlock. Like sender is waiting for receiver is waiting for sender. They both will keep on waiting. Nobody will progress. Okay, or no, nothing will happen. So that is deadlock. So how to deal with this deadlock? So for this, sender will maintain a timer. Okay, so the moment it sends the frame, it will start the timer. Okay, and when timer expire, what is the value of timer? Forget about it. We will study that later. So when timer expire, sender will send the frame again. Are you getting it? So that is the basic scenario. Okay, so error control, for error control, what we are doing, receiver will silently discard the frame. Okay, and when timer expire, sender will send the frame again. So the basic idea is that receiver is not instructing sender to send frame again and so on. It is simply, or you can say it is silently discarding the frame. Okay, so when timer will expire, everything depends on timer. When timer expire, sender will send the frame again. Okay, so we call this mechanism as automatic repeat request, ARQ. Why we are calling it as ARQ, automatic repeat request? Because sender is automatically repeating the frame. Okay, or you might think that automatically repetition request has come, because receiver has not explicitly mentioned that please send frame again and so on. Okay, so ARQ means automatic repeat request. Okay, this mechanism is used for error control. Okay, for error control, ARQ is used. ARQ means if there is error, receiver silently discard the frame. Receiver silently discard frame, and when timer expire, sender again send the frame. When timer expires, sender again send the frame. Okay, that is the basic meaning of ARQ, or automatic repeat request. Okay, that means receiver is not giving any instruction to the sender for retransmission. Receiver is not saying anything. Okay, receiver is simply silently discarding the frame, but sender, after timer expires, sender will send the frame again. Okay, that's why we are calling it as ARQ, or automatic repeat request. Please let me know if anybody is having any doubt. Let me write that, automatic repeat request. I think I have not written it. Yeah, ARQ means automatic repeat request. Yeah, take snapshot. I will jump to the next slide.
Done, sir.
Okay. So now 3 protocols we are going to study for flow and error control. What are these protocols? Take snapshot. I will jump to the next slide. Okay. So 3 protocols we are going to study for this flow and error control. What are these protocols? Stop and wait ARQ. ARQ means automatic repeat request. Next is go back and ARQ. And the last is selective repeat ARQ. Selective repeat ARQ. Okay. Stop and wait, go back, and selective repeat. So we are going to study these 3 protocols. Okay. Take snapshot. I will jump to the next slide and we will start our first protocol, that is stop and wait. Done?
Yes, sir.
Okay. So the first protocol which we are going to study is stop and wait. You can call it as ARQ. Stop and wait ARQ. Okay. As the name suggests, what we are doing, this is sender, this is receiver, and this is timeline. Okay. So time is going like this, like 10 a.m., 10, 1 a.m., 10, 2, 10, 3, 10, 2, 4, 10, 5, okay, and so on like this. So time is going like this. Okay. This is the timeline. So here what I am saying is sender will send one frame. After sending the frame, it will stop and wait for acknowledgement from receiver. Okay. After receiving acknowledgement from the receiver, it will again send a frame, and then again it will stop and wait for acknowledgement. After acknowledgement come from receiver, then it will again send frame, and so on like this. So as the name suggests, only one frame is sent by sender, and then it will stop and wait for acknowledgement. That's why it is known as stop and wait. Okay. So as the name suggests, you can write. Okay. One line if you want to write, you can write. As the name suggests, sender will send only one frame. Sender will send only one frame. Sender will send only one frame, and then it stop and wait for acknowledgement, and then it will stop and wait for acknowledgement from receiver, and then it will stop and wait for acknowledgement from receiver. Okay. So directly indirectly this means sender will send the next frame only after receiving acknowledgement. That means without receiving acknowledgement, it can never send the next frame. Please write that point. Sender will send next frame only after receiving acknowledgement from receiver. Sender will send next frame only after receiving acknowledgement from receiver. Okay. Yeah. Next, another point is, see, sender has sent frame to the receiver. So now it might happen that this frame is lost, or this frame is corrupted and receiver silently discarded. Some problem might happen. So sender will maintain a timer. Okay. So if timer expire, it has to send frame again. That means, see, if frame is lost in the medium itself, how it is lost, don't worry, we will tell you all these things after few lectures. But you might think that frame might be lost in the medium, or receiver has received the frame, but after applying error detection mechanism, it came to know that frame is corrupted. So receiver will silently discard the frame. Okay. And there might be some other reasons also. So the basic thing is that since receiver has not received the frame properly, receiver will not send acknowledgement to the sender. Okay. Or sometimes it may happen that frame is received by receiver properly. It has also sent the acknowledgement, but this acknowledgement itself has been lost in the medium. So there might be multiple cases. Don't worry, I will write them step by step. Don't worry, I am just giving you the explanation that sender has sent frame to the receiver. This frame is lost in the medium, or this frame is corrupted, or frame has been received fit and fine by receiver and it has sent the acknowledgement, but acknowledgement is lost. So whatever may be the case, sender has not received acknowledgement. That is the basic thing. Sender has not received acknowledgement in certain span of time or in fixed amount of time. It has not received acknowledgement. So after timer expires, so I have told you na timer will be maintained. After timer expire, sender has to send this same frame again. Now since sender has to send this same frame again, so how it will send? That means it has to maintain copy of the frame. Okay, so after sending the frame, do not think that sender will not maintain copy, because after sending he will become that okay, I have sent, forget about it and so on. No, it has to maintain copy of the frame. Okay, so after sending the frame, sender has to maintain copy of the frame, and immediately timer must be started, and after timer expire, it has to send the same copy again to the receiver. That is the basic scenario. Okay, so please write that point. Sender must maintain copy of frame. Sender must maintain copy of frame, and timer must be started after sending it. Sender must maintain copy of frame, and timer must be started after sending it. And timer must be started after sending it. When timer expires, and no ACK came from receiver, when timer expires and no ACK came from receiver, then it retransmit the frame. When timer expires and no ACK came from receiver, then it retransmit the frame. Okay, then it retransmit the frame. Okay, so when timer expire and no ACK came, then receiver from receiver, then it means sender. Then sender will retransmit the frame. Okay, so I think you have got the point. So 3 reasons for retransmission. What are the reasons of retransmission? 3 reasons of retransmission. I have told you clearly. What was the first reason? Frame lost. Frame lost in the medium. Frame is lost in the medium. How? Don't worry, we will tell you. Next, frame is corrupted. Frame is corrupted. Okay. Third is ACK is lost. Okay, that means frame received was fit and fine. ACK is sent from receiver to the sender, but ACK is lost in the medium. So whatever may be the case, we need to retransmit the frame again. So these are the 3 reasons for retransmission. Okay, yeah, and this is very, very important. If ACK is lost, what will happen? Let me tell you. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so this is sender, this is receiver. Sender has sent 1 frame. Receiver has sent ACK for it, but this ACK is lost. So this frame has been received by receiver properly. That's why it has sent the ACK, na? So this frame has been received by receiver properly. That's why it has sent ACK, but this ACK is lost in the medium. So when timer expire, sender will send the same frame again. But how receiver will come to know that it is the same frame which I have received already? So it will accept the same frame again. That means duplicacy of frame will come into the picture. Duplicacy of frame. Are you getting it? Receiver will receive the duplicate frame, and receiver will not be able to know that it is a duplicate frame and so on. So what is the solution? Solution is we should give sequence number to each and every frame. Okay. So solution to the problem is give sequence number to each and every frame. Give sequence number to each and every frame. Now question arises, if sender wants to send 1000 frames. Okay, so if sender wants to send 1000 frame, then what should be the sequence number? Okay, 1000 frame, the sequence number. What should be the sequence number? So you will say, sir, simplest solution is 1, 2, 3 and so on. You give sequence number like this. For first frame, you give sequence number 1, like frame 1, frame 2, frame 3, and so on, frame 1000. If you do like this, nothing is free in this world. If you do like this, so for 1000, how many bits are needed? For 1000, I think you already know, 2 power 10, no, 10 bits. 10 bits are needed to represent this 1000. I think you already know these things, or should I explain it why 10 bits are needed?
That's okay, sir. Yeah.
Okay, yeah. So for 1000 we need 10 bits. So indirectly this means that this 10 bit, and please do not say for 1 we need only 1 bit, for 2 we need 2 bits, for 3 we need 2 bits, and so on. So variable bits we cannot keep. Okay, so we have to keep this 10 bit in frame header. So this sequence number free, nothing is free now. So how you will represent this these sequence numbers? So to represent this sequence number, you have to reserve 10 bits in frame header. So frame header 10 bits reserved. Frame header 10 bits reserved. Okay, now do not say in first frame you reserve 1 bit, in the next frame you reserve 2 bits, and so on. We cannot do like this. Okay, so we have to do lots and lots of programming for this kind of thing, and anyway this is not feasible also. So better is you keep fixed number of bits in your frame. So frame header 10 bits are reserved. So now obviously this is a very huge overhead. We have to send 1000 frames, 10 bit overhead in each frame. 10,000 bits you have wasted just because of this sequence number. Okay, that is not a good idea. Now why this is not good idea? Because sender is sending only 1 frame and it is waiting for acknowledgement. Then sender is sending another frame and it is waiting for acknowledgement. Like this they are doing. So only 1 by 1 we are sending frames. So why you are wasting 1000 sequence numbers and so on? Okay, so better is you reserve only 1 bit for sequence number. 1 bit means frame number 0, frame number 1. That's it. Okay, so if you want to send 1000 frames, take snapshot. I will jump to the next slide.
Done, sir.
Okay, so if sender wants to send 1000 frames, like 1, 2, 3, 4, 5, 6, and so on. So what will be the sequence number for first frame? It will be 0, then 1, then 0, then 1, then 0, then 1, and so on like this. Okay, are you getting it? So frame number 1, sequence number 0. Frame number 2, sequence number 1. Frame number 3, sequence number 0. Frame number 4, sequence number 1, and so on. We will do like this. So now why we are doing so? Because sender is sending only 1 frame and it is waiting for acknowledgement. Okay, this is sender, this is receiver. Sender is sending only 1 frame. It is not sending multiple frames. Okay, sender is sending 1 frame and it is waiting for acknowledgement. Then sender is sending next frame and it is waiting for acknowledgement. Like this we are doing. Okay, is it okay? Yeah. So that's why we have reserved only 1 bit, and it will cover all the possibilities. Okay, like if frame lost, acknowledgement lost, whatever may be the case. Okay, we are able to handle all these scenarios. Okay, so if frame is lost, no problem. Let me tell you the scenarios. What if frame lost? Okay, what if ACK lost? Okay, and what if ACK is delayed? We will study all the scenarios. Okay, so frame lost. Frame lost means sender receiver. So frame number 0, it has sent, it is lost in the medium. So obviously after timeout, sender will send again frame number 0. So there is no problem at all. Okay, here there is no problem. When frame is lost, no problem. What if ACK is lost? So this was the big problem which we were not able to handle, and that's why we have used the concept of sequence number. So if frame number 0 is sent from sender to receiver, okay, then what receiver will say? Receiver will say acknowledgement. Okay, so we have given numbers to the frame, we have not given numbers to the acknowledgement. We are assuming that acknowledgement is only one and the same only. Okay, for every frame we will send same acknowledgement. I am assuming that. Okay, later I will change it, but I am assuming that acknowledgement is same. So frame number 0 we have sent and acknowledgement is sent for the frame. Okay, now assume this acknowledgement is lost in the medium. So receiver has received frame number 0. So now what sender will send again? Obviously it will send frame number 0. So receiver will say, I have already received the frame number 0. Why you have sent it again? So it will say, okay, it is duplicate and problem solved. Okay, so no need to worry. Okay, and what if acknowledgement is lost? Okay, what if, sorry, acknowledgement lost is okay. What is acknowledgement is delayed? Delay acknowledgement means like this. This is sender, this is receiver. sender has sent frame number 0. This ACK, it has you can say it has sent, the receiver has sent the ACK, but it is delayed. Delayed means timeout has already occurred. Okay, so sender has sent this frame number 0 again. Now it will send the ACK. It will send the ACK. Now it will send frame number 1. Okay, why? Say I think you have got it, na? Frame number 0 receiver has sent. Now sender has sent frame number 0, receiver has sent ACK for it. Now ACK, it is temporarily delayed. It has not yet come. So but before receiving acknowledgement, timeout occurred. Because timeout occurred, that means what? Timer has expired. Timer expired, so sender will send again frame number 0. So receiver will obviously, you can say it will say frame number 0 I have already received. It is duplicate frame, so it will simply discard. It will simply discard it, and receiver will come to know, okay, it might be the case that my acknowledgement has not been received by a sender. That's why it has sent frame number 0 again. So obviously it will send ACK again. Are you getting it? It will send ACK again. Okay, so now sender has received that acknowledgement. Now it will send frame number 1. Sender will send frame number 1 to the receiver. Now assume this ACK come. Okay, and assume that frame number 1 is lost in the medium, or it has not been received, whatever may be the case. This acknowledgement come to the sender. Now sender will be confused that what has happened. It will say, okay, frame number 1 has been received by receiver properly, so it will send the next frame number 0, but receiver will say, I have already received frame number 0, why you are sending it again? It will simply discard it. But actually it is not duplicate frame, it is the next frame which is coming into the picture. That means it is a very big problem. So what is the solution? Solution is that acknowledgement should also be numbered. Not only frame should be numbered, acknowledgement should also be numbered. Okay, so sequence number should be given to frame also, and it should be given to acknowledgement also. So earlier we have not studied this, and now I am explaining you that why acknowledgement should also be numbered. So now take snapshot. I will jump to the next slide, and I will give you the proper explanation of what will happen in these scenarios. Take snapshot.
Done, sir.
Okay. So now what we will say, this is sender, this is receiver. So frame number 0 it has sent. So now what receiver will send? You have to remember this thing. What receiver is expecting? What receiver is expecting? That is ACK number. So frame number 0 has been received by receiver. So what receiver is expecting now? Frame number 1. So it will send ACK 1. Okay. So it will send ACK 1. The moment sender receive ACK 1, it will say, okay, receiver is expecting frame number 1. So let me send frame number 1. Okay. So now what receiver is expecting? Frame number 0. So it will say ACK 0. So okay, sender will send frame number 0. It will send ACK 1, and so on. Are you getting it?
Yes, sir.
Okay, that is the basic scenario. So now we will study that what if acknowledgement is delayed and so on. Delayed acknowledgement, I am explaining you. Let me write it. Delay acknowledgement. Delay ACK.
We
So
discussed this one now, sir.
sender has sent frame number 0. Now receiver has sent ACK 1, but it is temporarily delayed. So what will happen after timeout? Sender will again send this frame number 0. Receiver will say it is duplicate. So it will discard it, and it will come to know that sender has sent frame number 0 again. That means it might be the case that my acknowledgement has not been received. So it will send acknowledgement 1 again. Now sender will receive this acknowledgement, and it will send frame number 1. Since it has sent frame number 1, and let us assume that this ACK 1 now come into the picture, and sender receives this acknowledgement number 1. Now what sender will say? Sender will say, no, there is some problem, because I have just sent frame number 1 So ACK 0 should come. How this ACK come into the picture? How this ACK 1 has come? So sender will say no, I think it is a delayed acknowledgement and so on. So it will simply reject that acknowledgement and it will keep on waiting for ACK 0, which will be actually sent by receiver to the sender. Are you getting it?
Yes, sir.
Okay, please let me know. This is a bit difficult type of concepts. If anybody is facing any difficulty, please let me know. I will explain it again. Yes, any doubt in anybody's mind?
Nice, sir.
Okay, okay, good. So take snapshot. I will jump to the next slide.
Done, sir.
Okay. So now I will discuss few questions. These questions have been asked in GATE many times. So if sender wants to send 10 packets, sender wants to send 10 packets using stop and wait. They will properly mention in the question. Sender wants to send 10 packet using stop and wait. I'm writing shortcut. Okay, but they are saying every 5th packet is lost in the medium. But every 5th packet is lost in the medium. So total number of packets sent. Total number of packets sent we want to find. Are you getting it? Sender wants to send 10 packet using stop and wait, but every 5th packet is lost. What is the total number of packets sent? So it is very simple. 1, 2, 3, 4. 5th packet is lost. So 5th packet is lost. So obviously it has to send 5th again. 6, 7, 8, 9. So how many packets it has sent? 1, 2, 3, 4 and 5. So again this 9 will be lost in the medium. Let me write it with red color. 9. So now it will send again 9 and 10. That's it. So 5th packet will be lost. Now this is first, this is second. So obviously they will be received properly. So how many packets you have sent? Total 12 packet you have sent. So in place of sending 10 packets, sender will have to send the 12 packets. Why 12 packet? 1, 2, 3, 4, 5. 5th packet is lost. Then again you start counting 1, 2, 3, 4, 5. 5th packet is lost. Now again you start counting 1, 2. No problem. 5th packet will be lost. No? So the next other coming packet will be lost. So no problem. So totally you have to send 12 packets. Okay. So if sender wants to send 10 packet, every 5th packet is lost. So it has to send 12 packets. Okay. Yeah. And let us assume for the same problem, if they say every 4th packet is lost, what you will do now? Every 4th packet is lost. Every 4th packet lost. So what you will say? You simply say 1, 2, 3, 4th packet lost. Then again 4, 5, 6 and 7. 7th will be lost. Then again 7, 8, 9, 10. 10 will be lost. So you have to send 10 again. So total how many packets? 13. Please let me know if anybody is having any doubt here. So are you able to see now how I am doing counting? 1, 2, 3, 4. 4th packet lost. Then again 1, 2, 3, 4. 4th packet lost. Then 1, 2, 3, 4. 4th packet lost. Yes. Please let me know if anybody is facing any difficulty.
Nice, sir.
Okay. Take snapshot. I will jump to the next slide.
Okay, sir.
Okay. So next is GATE 2006 question I am going to discuss. So they are saying probability of error. Probability of error is 0.2. Okay. In medium. They are talking about wireless media. So I am writing in wireless medium. Okay. So probability of error is 0.2. And what they are saying? Average number of transmission attempts. Average number of transmission attempts required to transfer 100 packets using stop and wait. So this is clearly probability type of question. So don't worry, we have studied discrete mathematics, so we should be able to answer this question easily. So probability of error is 0.2 in wireless medium, and average number of transmission attempts required to transfer 100 packets using stop and wait will be. So what they are saying, we have a sender, we have a receiver, this is the medium, and here probability of error is 0.2. 0.2 means what? 20%. 20% error. So you will say we want to send 100 packets, 20% is the error. So 100 plus 20, that is 120 is the answer. And this is the first option which you will find in GATE, but this is wrong. Why this is wrong? Because error chances are 20%. Na? So you have taken 20% of 100, that was 20. You have to take 20% of this 20 also. How you have skipped that? Okay, so 20% of 20 will be what? 20% of 20 will be 0.2 into, it will be 4. So you will say 100 plus 20 plus 4, because 20% of this, now again 20% of this, now again 20% of this, and so on. So you will fall in infinite loop. Are you getting it? So how you will answer this question? So that is, so assuming, we will say, assuming sender wants to send n packets. If sender wants to send n packet, because of this n, you will say you have to add p multiplied by n more packets. Are you getting it? Probability is 20%. Now 20% of 100 you have added. 20% of 100 was 20. That is what you have added. So now this you have added. So now you will say for this number again 20%. So p. So p multiplied by n you will say. Now this you will say p multiplied by p multiplied by p multiplied by n. Are you getting it now? Double p n as it is p multiplied, and so on till infinity. So what I will say? I will take n as common, n plus p square plus p cube dot up to infinity. Clearly we are talking about probabilities. So probability is obviously 0.2 and so on, they will give you like this. So probability will be less than 1. Na? So if less than 1, and this is what GP, sum of GP, and here P is less than 1. So sum of infinite terms is what? 1 upon 1 minus 1 upon 1 minus P you will get. Are you getting it now? For infinite terms, 1 upon 1 minus R na? As infinity. We have studied this in discrete mathematics while studying generating functions and all. Okay, and this is very simple also. Infinite terms summation is 1 upon 1 minus R. That is common ratio. Common ratio is P here. So 1 upon 1 minus P we will get. So n is common. N upon 1 minus P. N upon 1 minus P. So what is this n? We want to send 100 packets. So 1 upon 1 minus P. What is this P? P is 0.2. So 100 upon 0.8. So here we will get this 125. So 125 is my answer. So I have told you many times, na, in GATE you will not find question from single subject. They will mingle up the subjects. Like they have now mingled up discrete mathematics and your computer networks. So basic mathematics you should know. Okay, only then you will be able to secure good rank in GATE, because you will keep on studying networking, you will keep on studying basic concepts in networking, but they will ask such kind of question which will definitely confuse you. You will not be able to answer such question unless you know these probability concepts and so on. Okay, take snapshot. I will jump to the next slide. So this question was more related to probability, but they have asked in computer networks. Okay, yeah. Take snapshot. I will jump to the next slide. Okay. So next we are going to start efficiency of stop and wait. Efficiency, again very important. Many questions have been asked. Efficiency of stop and wait. Okay. So what is efficiency? Efficiency is represented by eta, like this. Efficiency. Efficiency is useful time upon total time. See, I will say in your entire day you have studied for 12 hours, so you will say your efficiency is 0.5, because total is 24 hours and from that you have studied 12 hours, so your efficiency is 0.5. Like this you will say, so useful time upon total time, useful time upon total time, that is the efficiency. Now this is sender, this is receiver. What is the useful time? That means for how long sender was busy. It was sending data, na? For that amount of time only it was busy. So what is that time? That is transmission time only. Transmission time is message size upon bandwidth, na? So that means senders keep on sending data for transmission time only. So sender was busy for transmission time only. Okay, for rest of the time it is idle. As the name says, stop and wait. After sending one frame, it will stop and wait for acknowledgement from receiver. Once it has received acknowledgement from receiver, only then it will send the next frame and so on. Are you getting it now? So that is creating problem for us. That's why efficiency of stop and wait will be very, very less. Why? Because after sending one frame, sender will keep on waiting for acknowledgement. Okay, after receiving acknowledgement, only then it can send the next frame. So that will create problem. So useful time is what your only transmission time. So let me draw that diagrammatically also. You will get more clarity. So this sender has sent one bit. So this one bit, it will take some amount of time to reach to the receiver, and it has sent other bits also. So like this. So till this point, sender has sent the data. So last bit will also need some time to reach the receiver. Okay, so this was the TT time, transmission time for the sender. Okay, so first bit has already taken this time, that is TP time. So TP time is taken by receiver to receive the first bit, and then after TT time, receiver has received the entire frame. So TP plus TT time, that is the time in which receiver has received the entire frame. Now it will send the acknowledgement. Okay, it has received the frame, it will send the acknowledgement. But see, I am drawing like this. I'm not drawing like this. Why I'm not drawing like this? This means that at this point, at this time, receiver has sent the acknowledgement, and at the same time sender has received it. No, there is some delay. That is propagation delay or TP time. Are you getting it now? These are the timelines. So I'm not drawing like this. This means what? At 10 a.m. receiver has sent the acknowledgement, and at 10 a.m. only receiver has at 10 a.m. only sender has received the acknowledgement. No, it is never possible. Okay, so you have to draw like this, slanting. That means at 10 a.m. it has sent the acknowledgement, and at 10:05 a.m. it has received the acknowledgement, like this. That's why I have drawn slanting line. Okay, so at this point of time, it has received the acknowledgement. Okay, so what is this time? This time is again TP time. Are you getting it?
Transmission time, sir, or?
No, only propagation time we will take, na? Why? Because a receiver has sent the acknowledgement. So acknowledgement one bit delay. See, yes, if acknowledgement is very big, so it will keep on sending acknowledgement like this. Yes. So this will be the TT time of acknowledgement, but I am not taking TT time of acknowledgement just because I am assuming that acknowledgement is very small, or you can say one bit acknowledgement. Okay, otherwise you have to take TP time of acknowledgement also into the picture, which I am not taking. Okay, so that's it. So now what is the total time? So how we will answer? So useful time. So useful time, efficiency is useful time upon total time. So what is your useful time? Useful time only the transmission time of the packet. Transmission time. What is the total time? So first TP time. TP time for the first bit to reach at receiver, and then TT time for the packet to be received, and then again TP time for acknowledgement. So TT upon TP plus TT plus TP. Okay, and I am again and again saying I have ignored the transmission time of acknowledgement. Why? Just let me draw it with another color so that you get more clarity. So this should be the transmission time of ACK. Okay, but I have ignored it just because I am assuming ACK is of 1 bit only. So TT ACK ignored. Otherwise, I have to add here TT ACK also. Okay, but I am ignoring that. Anyway, I will solve many GATE questions. Don't worry, you will get more clarity. In GATE exam, every type of question has been asked. That is the beauty of GATE exam. They will ask each and every type of question. Don't worry, I will discuss all of them. Don't worry. But for basics questions or for simplicity, I have taken this scenario that TT upon TP plus TT plus TP. That is the basic thing. That is the efficiency. Okay, so you can divide numerator and denominator by TT. What you will get? So this will become 1 upon 2 TP upon TT plus 1, or 1 upon 1 plus 2A, where A is TP upon TT. This is the efficiency of your stop and wait. Very, very important formula. 1 upon 1 plus 2A. That is the efficiency of stop and wait. And my suggestion will be, don't go by formula. I have just derived it so that if they by chance ask a question, anyway chances are very less that they will never ask what is the formula of efficiency and all. GATE will never ask such type of question. But if by chance they ask, that's why I have given you that this is the formula 1 upon 1 plus 2A, where A is TP upon TT. They will be very, very big numericals. Okay, they will give you big numericals. They will not say what is the formula of efficiency and all. It is not your university exam where they will give you what is the formula, or they will give you some data and you put that data and you will get the answer. Apply the formula, get the answer. That is not GATE. Okay, they will not ask these questions. They will ask you very good questions. I will come to that. Don't worry. I'm just building the basics here. Take snapshot. I will jump to the next slide. Yes, done. Okay, so 1 upon 1 plus 2A, we have got it. So that is the efficiency. Okay, and sometimes we can say like this also, TT upon 2 TP plus TT. 2 TP means 1 bit delay from sender to receiver, from receiver to sender. Both we have added, that is 2 TP. Okay, so this is known as RTT, or round trip time. So sometimes they will say RTT also. So don't worry, RTT means 2 TP. Round trip time. Okay, 1 bit from sender to receiver, 1 bit from receiver to sender, both. If you take, that is 2 TP, that is nothing but RTT. So your efficiency will become TT upon RTT plus TT, like this also. Okay, yeah. Take snapshot. I will jump to the next slide. Done. Yes, any doubt?
No, sir.
Okay. Yeah, so next is throughput of stop and wait. I am just deriving the formulas and then I will show you the questions. Throughput of stop and wait. What is the throughput? Throughput, I think I have told you in the previous lectures also. Actually, how fast we can send data. Actually, how fast we can send data. That is known as throughput. Okay, for example, bandwidth is 1 Mbps. Line bandwidth is 1 Mbps. Here we have sender. Here we have receiver. Bandwidth is 1 Mbps, but sender can send data at 200 kbps and receiver can receive data at 200 kbps. Okay, sender send at 200 kbps, receiver also receive at 200 kbps. Line bandwidth is 1 Mbps. So what is the use of this 1 Mbps? We cannot use it. We will have to send and receive data at 200 kbps only, and that is nothing but your throughput. I have told you in the previous lectures also. So throughput means actually how fast we can send data. Bandwidth is potential measure of link. That means how much, what is the upper limit? What is the upper limit? That is the bandwidth. Okay, but actually how fast we can send data, that is the throughput. Okay, yeah, I have told you many times. Yeah. So what is the throughput of stop and wait? Let me tell you that thing. So assume packet size is P. Assume packet size is P. Packet means frame. So assume frame size is P. So now to send this P byte, Okay, to send this p bytes, or let me take it bits just for the sake of simplicity, because you have to multiply it by 8 and so on. So packet size is p bits. Now to send this p bits, what amount of time you have taken? tt plus 2tp. Are you getting it now? See this was the total cycle time now. tt time plus 2tp time. In this time, sender has sent one frame and it has received the acknowledgement. Are you getting it? So see this, sender receiver, sender sent one frame and it has received acknowledgement. So this total time is tp plus tt plus tp. So tt plus 2tp. Okay, tt plus 2tp, this is the total time, okay, to send this frame. Okay, rather frame has sent and it has received acknowledgement. So I will say total time to receive this frame successfully by receiver, that is 2tp plus tt. So that's why I have written here, in tt plus 2tp time you have sent p bits. So in 1 second, how many bits you have received, or how many bits you have sent? P upon tt plus 2tp. Please let me know if anybody is having any doubt here.
No doubt, sir.
Okay, yes. So now let me change it a little bit, but I will say packet size upon bandwidth multiplied by bandwidth. I have just multiplied and divided by bandwidth, and here we have tt plus 2tp. Bandwidth will be cancelled, no problem. But why I have added this? Just because message size, that is packet size or message size, one and the same thing. Message size upon bandwidth is transmission time. So I will say transmission time upon transmission time plus 2 into TP time multiplied by bandwidth, and that is nothing but, I have just explained you, efficiency. That will be efficiency multiplied by bandwidth. So what is the throughput? Throughput of stop and wait is efficiency multiplied by bandwidth. Yes. Please let me know if anybody is facing any difficulty. Any doubt here?
Sir, how packet upon bandwidth is transmission time?
Packet size upon bandwidth, I have told you in the previous lectures also. Message size upon bandwidth is what? Transmission time.
Okay, sir, understood.
Yes. So I hope everything is fit and fine. So in the next lecture, please try to revise all the things. In the next lecture, we will solve gate questions one by one. I will solve many gate questions so that you get more clarity about problem solving on stop and wait. Okay, we will solve at least 4 to 5 questions in the next lecture. This is very important topic. Many times questions have been asked. So 4 to 5 gate questions I will solve in the next class. Okay, and in the next class itself we will try to complete this stop and wait, and we will jump to the next go back and selective repeat and so on. We will study these only. Okay, yeah. So I hope everything is fit and fine. So I will stop here itself. Okay, in the next lecture we will start with numericals only. Okay then. Okay, good night, bye bye.